we live in a very complex solar system. We have a star, we have some large bodies, and we have a bunch of medium, small bodies, and we have a lot of debris. If you were to break up the solar system into zones, you can consider zone 1, the inner solar system, to be containing these 4 bodies right here: Mercury, Venus, Earth, and Mars. These are the rocky worlds of our solar system. Zone 2 would extend from the asteroid belt out to about 30 astronomical units, where 1 astronomical unit is the average distance between Earth and the Sun. And it's composed of Jupiter, Saturn, Uranus, and Neptune. And zone 3 is the new zone, if you will. It's where the Kuiper belt is. This is the zone we know the least about. We've had several space probes go through it. The Voyagers have gone through it, the Pioneers have gone through it, but they've returned really nothing other than some solar wind data. And now we have a space probe in the Kuiper belt that's purposely sent to explore the Kuiper belt. And the first object it was to explore was Pluto. So the Kuiper belt is here. It's about 30 to 50 astronomical units out from the sun. It's comprised of millions of small bodies. Short-term comets come from here. There's probably on the order of thousands of bodies that are large enough to be round, so what you would call a dwarf planet size. And the first one that we discovered, is the one we now call Pluto. So Pluto was discovered by this gentleman right here, Clyde Tombaugh. He was charged by Percival Lowell to look for the next planet out from Neptune. They believe there's another planet out there, and there's a race to see who could find it first. So Clyde looked at plates, these glass plate exposures that were taken, and he would look at ones taken in the same part of the sky over a period of days and do what we call a blink. So he'd illuminate one, and then the other would be overlaid, and the first one would be taken out of the field of view, and they would blink back and forth. And anything that moved in there, he could then start measuring. So he found asteroids, he found at least 1 or 2 comets, he found all kinds of things while he was doing this, and he found this body that was out beyond Neptune's orbit, right here. They did some orbital calculations, and they discovered it's a bit of an oddball. It was much more elongated orbit, elliptical orbit, than most of the rest of the planets here. The plane of its orbit was tilted much more than the rest of the classical planets here. But since they didn't know what else to call this, we're going to just lump it in with what we call planet. So the orbital inclination is like 17 degrees. It orbits the sun in about just under 250 years, and it's fairly small. When it was first discovered, they didn't have a name for it, but it was the news around the world was they discovered a new planet, and the astronomers at the observatory were going back and forth debating what should we call this thing. This news got out, and young girl in England, in Oxford, England, was having breakfast with her parents one day, and her father read the news dispatch that was in the paper and mentioned that they didn't have a name for it yet. And Venetia Berti here, who was versed in the classical mythologies of the Greek and Roman pantheons, suggested, well, why don't they call it Pluto? Because it would fit in with the rest of the planets. So her father then told an astronomer friend of his, and he then passed it on to the observatory. And Clyde Tombaugh heard about this and said, you know, I like it because not only does it stick with the pantheon, but the first 2 letters of Pluto are Percival Lowell's initials. So Pluto's really, really far out there. If you were to take a car, it would take you just under 7,000 years to go at highway speeds to get out to Pluto. A bike would take you a little bit longer. But New Horizons kicked it in 9.5 years. So what more do we know about Pluto? We know it's round. We know it's odd compared to the rest of the classical planets, but at the time when we didn't know anything else, so we called it a planet, And then we started finding more and more and more objects out there that were on the order of Pluto. Most of them were smaller. One of them, which fired off the whole debate of, okay, what exactly is a planet, was Eris. When it was first found, it was thought to be just a few % larger than Pluto. It's since been determined that Pluto's still a few % larger than Eris, but they're essentially identical size. And so there's this whole debate that went on with the IAU and with the astronomy community and the planetary scientists sub-community of the astronomy community about what a planet is. For purposes of this talk, if it's round and it goes around the sun, it's a planet. How's that work? So, yeah, I just mentioned 2006 is when the IAU came up with their somewhat convoluted definition of planet and dwarf planet. So we will consider dwarf planets to be a subset of planets because we have rocky bodies, which are a subset of planet, and gas giants, which are a subset of planets. And if you can work with that, and you consider dwarf is a classification, not a demotion, because our sun's a dwarf star, and still called a star, I think we're good. So over the years then, we've learned that there's a host of bodies that are accompanying Pluto around its orbit on the sun. 4 of these are moons, and then we have Charon right here. We discovered 2 of these moons after we launched New Horizons, which caused us some concern while we were flying out towards it. Charon is the largest companion to Pluto. It's about 1/8 the mass of Pluto. It orbits, when the orbit is basically tidally locked to Pluto, so they basically orbit each other. They orbit this point right here called the barycenter, which you can see also right here, they're going around each other. So Charon is not technically a moon of Pluto. The other bodies orbit Pluto itself, so they're considered moons. So Pluto basically is the only binary planet system that we have in our solar system, and in that state is even more unique than anything else that we've seen. So Pluto is also faint. These numbers here, for those who are not familiar with the magnitude system, is the brightness of the stars. The smaller the number, and it goes into the negatives, the brighter the star is. So like our sun, if you go out and look at it during the day, it's considered -26 magnitude. The full moon is -12 magnitude. Venus at the brightest is -4th magnitude. Jupiter at its brightest is about -2.5 or so. And as you get smaller, your naked eye on a good night, if you have good eyes, can see down to about 6th or 7th magnitude. You have a good, clear, light pollution-free sky, it's nice and dark, you can see about that far. Pluto pushes around 13th or 14th magnitude. It's not visible to the naked eye. And if you were to just take an image of it, unless you knew exactly where you were looking, you had a good star chart to go with it, you would not be able to pick it out unless you took multiple images and saw it move against the background stars. So, now, New Horizons. This is the makeup of the spacecraft here. The different instruments are pointed out here. And to give you an idea of scale, that's there's a couple guys in the clean room checking out the spacecraft here on this palette. New Horizons was over a decade in coming. Alan Stern was a member of what they call the Pluto Underground. There's a team of scientists who said, you know, we've had missions go to Mars and Venus, and Mariner 10's gone to Mercury, and we've had missions go to Jupiter and Saturn, and for crying out loud, even Uranus and Neptune, but nothing has visited Pluto at this point. So they got together and they proposed it back in 1990, Pluto 350. That almost flew, but didn't quite. NASA said, yeah, that sounds like a good idea, but now we're going to pull the funding on it. And then they tried a year later to the Pluto Mariner Mark II. And then a year later to Pluto Fast Flyby, and so on and so forth. And every turn, they would either get approved, and then the funding would be cut, or they wouldn't even get through the proposal process. Until 2001, when New Horizons was proposed, and NASA awarded the grant money to APL, the Applied Physics Lab where I work, up in Maryland, and to SWRI, the Southwest Research Institute, who joined together to make this proposal where Alan Stern works. And within a few years, we got it turned around and launched. The cost of the mission is a very low level cost. It costs less than your average football stadium does now to run the whole mission from inception to last year when we did the flyby. The mission operations are run at the Applied Physics Lab up in Laurel, Maryland. This is our pit here, our flight operations center here. And as a little bit of a trivia for you, when Clyde Tombaugh was alive, he knew about the mission. He said, you know, if anything, I would love to go visit Pluto. If I wanted to visit any planet, I want to visit Pluto. He died, but Alan Stern contacted his kids and said, hey, we're going to be sending the space probe to Pluto. Can we get some of Clyde's ashes? And his son and daughter gave him a small container here of Clyde's ashes, and we bolted it inside the spacecraft. So Clyde is the first person to have visited Pluto, and if before too long, he's going to be the first one to leave the solar system. Or at least a part of it, anyhow. If you walk into a fancy hotel lobby and you find a baby grand piano, that's the size of the spacecraft. So if you got a feel for how big a grand piano is, that's how big the spacecraft is. It's not real large. It carries a lot of instrument power on it and a lot of other instrumentation, not just for scanning the planet, but you know, computers, the power plant, the whole 9 yards. It has, it's powered by a radioisotopic thermal and electric generator. It carries 7 science instruments. It has 2 solid-state recorders, and they were, after July, pretty much full from the flyby last year. This is the RTG here, sticking out the end of the spacecraft. The science instruments here, Lori, Rex, Ralph, and Alice. Ralph and Alice are not actually acronyms. Most everything else, you know, NASA loves acronyms, like the military loves acronyms. Ralph and Alice were named specifically after 2 characters from the TV show The Honeymooners. The other 3 instruments are Pepsi, SDC for Student Dust Collector, and SWAP. SWAP is the instrument that I work with, but the SDC is really interesting in that it is the only student-designed and built instrument, fully student-designed and built, that's on a spacecraft and is still operating. Every other instrument that had student involvement has had student involvement. In this case, the students here were overseen, advised by this gentleman right here, and the rest of the students designed it, built it themselves. And a number of them are still following the New Horizons spacecraft and using the data that they're getting back from that in their research. The flyby was a once-in-a-lifetime thing. We weren't going to get a second shot at this. So we had to make sure that all this we were going to be able to do. So we launched in January 2006, barely 5 years after we got approval from NASA to go ahead and do the New Horizons project. We flew past the moon in 9 hours, which is relatively fast. Pioneer 10 took 11 hours. To get to Jupiter, it took us 13 months. You can see Pioneers 10, 11, about 20 months, Voyagers in the 17 to 23 months. Galileo and Cassini took years, but then they weren't flying by, they were going to actually go into orbit. So they went a little slower. So about 9 months after we launched, we turned the LORRI camera towards Pluto and took some images to see if we could actually detect Pluto from this far out. And you can see that dot right there is Pluto. So 13 months after we launched, we flew past Jupiter. And the reason we flew past Jupiter was to get a gravity boost in order to get us out to Pluto faster. As we're flying out from Earth, the sun is pulling on us, even though we're going fast enough to escape the gravitational pull of the sun completely. It would just slow us down more and more as we went out. Doing a flyby past Jupiter, we were able to pick up enough speed that we were able to trim off about 5 years from the mission. to get there last year as opposed to 4 years from now. But in addition to doing the flyby, we used Jupiter to exercise the instruments and do a pretend flyby of Pluto, except it's a really large Pluto as opposed to a small Pluto. And we took a bunch of images. Here is, some of you may be able to see this volcanic plume that's erupting. It's a 10-image GIF that we put together. This is my personal favorite image, is Europa rising over the limb of Jupiter. And that was the trajectory that we took when we flew past Jupiter. And communicating with the New Horizons, we use the Deep Space Network. There's 3 sites of the Deep Space Network scattered across the globe. There's one in Canberra, Australia, there's one in Madrid, Spain, and there's one in Goldstone, California. They're about 120 degrees apart on the globe. Here, here, here. They have a suite of 34-meter dishes and a single 70-meter dish, which all spacecraft that are doing interplanetary exploration utilize this communication network. So we have to apply for time to use any of the dishes here to communicate with our spacecraft, as does every other spacecraft out there. When we were doing the flyby, we were able to, because of this one-off event, get more time than most spacecraft. And other spacecraft actually gave up time that they had so we could make sure that we would get the critical data that we needed just before and after the flyby. And at this point in the game, things have balanced back out again. We're only getting a few hours a day, and other spacecraft are getting more time now. So we had a lot of time to plan. We had 9 years to plan for this encounter. One of the things we needed to know was, where's Pluto? I mean, we can look at a star map and say, oh, it's right here. But how do you tell a spacecraft that was launched 9 years ago that's been traveling on this arc that it's got to be over here and not over here? So our nav team had to plot all this out. We had to know very, very closely where we were going to be when we intersected with Pluto. We didn't want to land. That would be bad. But we didn't want to miss either by flying too far away, because we wouldn't get very much information. So we had a very small box. It was on the order of maybe a couple 100 kilometers square of where we wanted to fly through next to Pluto. And we had a very specific time window in which to do this. And we had a slot in the schedule, starting from 9 years ago, of about 2 minutes, plus or minus 2 minutes, about hitting that dead point. And we had to be able to plan everything ahead of time, because the sequence that we had to put to the spacecraft had to be uploaded weeks ahead of time. And it had to be ready to go days before we got to Pluto. So the sequence itself was about 2 weeks long, the whole sequence of commands. And we would not be able to do anything with the spacecraft in that time. The spacecraft is too far away to joystick. Hubble, we can joystick Hubble because it's right in orbit around Earth. The time delay between sending a command to Hubble and back is about 1.5 seconds. Once you get to interplanetary space, you're talking on the order of minutes to New Horizons on the order of hours. It's 4.5 hours one-way light time for communication with the spacecraft. So we send a signal out. It's going to take 4.5 hours to get there. It's going to be another 4.5 hours before we get a return reply. So if we were to try and joystick the spacecraft, we'd have to plan 9 hours ahead of time what it's going to do. So, and since the schedule is built to track everything down to like the 1/10 of a second, it's a very complicated routine and schedule that we have to do. Also, we plan for contingencies. What if something goes wrong with either the encounter? What if the backup computer has a hiccup? What if we start losing more power than we anticipated? What if the instruments start safing? There's a lot of what ifs. We had hundreds and hundreds of what-if scenarios to practice. And honestly, 9 years was not enough time to practice them all. The approach here, we started getting more concerned when we started detecting more bodies circling around Pluto. Right before we launched, we knew about, well, Charon and a couple of the others, but then we found 2 more. It's like, wait, aren't there even more bodies there that we can't see from Earth? Are we going to hit something when we get there? This would be bad, because it'll be all for all or nothing. So what we did was we planned the encounter so that Charon was on the far side from Pluto to make sure that this area was as clear as we could possibly anticipate it to be. We knew what the mass of Charon is, we knew the mass of Pluto, we figured out what the mass of everybody else was. So we were hoping this area here would be free of any debris, because flying at 33,000 kilometers an hour and you hit something the size of a golf ball, game over. So we went through all kinds of contingencies, we went through various tests, we continued doing burn updates, knowledge updates. We're just telling the spacecraft where it is in the solar system relative to everything else as everything's moving. We had what we call green card testing, which there was a team of people who dreamed up problems. And then they would randomly email a team saying, okay, this just happened. You need to drop whatever you're working on now and fix this. So, like my team would get an email that says, your instrument just saved. What are you going to do? And we would just have to drop whatever we're doing, because if it really happened in real life, we'd have to drop whatever we're doing anyhow. And we'd have to come up with a solution, try and figure out what happened, not in that order, and then upload the correction to the spacecraft here in a simulator. And the green card team was evilly gleeful about the things they came up with. So, like I said, we had hundreds and hundreds of scenarios to practice and to test for. And there's not enough time, even in 9.5 years, to test them all. Barely 10 days before the encounter, we had one hit that we had not tested, that was on the books to be tested. Was, what if the main computer reboots? What do we do? So July 4th weekend, remember last year was a beautiful weekend, everyone's out having their barbecues or picnics or doing whatever. I was in Western Maryland, rock climbing, out of contact with everybody. Came back. Meanwhile, we had some people at work who were monitoring the spacecraft. And my one friend there she's the lead flight control person. She was monitoring the communications with the Deep Space Network and the spacecraft. And periodically the telemetry will drop out. A few seconds later it will pick back up. So we know to expect this. So she's working on some documents, she looks over, okay, it's going, looks over, no telemetry. There's still no telemetry. Oh, now this is bad, we still have no telemetry. After 10 seconds, it's basically panic mode. We had no communication with the spacecraft. She started making phone calls and sending emails out to the team. The engineering team, who was available, responded right away. I had no cell signal where I was. I didn't learn about this until that evening when I got back. Anyway, back in the Flight Operations Center, we had lost comms for about 90 minutes. One of the engineering team came in and he said, okay, what time did you lose communication? And she told him what time. He said, okay, if things go as they should, if the spacecraft went into safe mode and the backup computer, the primary computer's had a problem and the backup computer kicks in, we should get a signal from it in about 90 minutes from the time you lost communication. 90 minutes later, we got a signal. So we were very happy about that. We weren't happy that when we learned that the primary computer, not only was it rebooted, it had nothing loaded in it. What had happened was we had copied everything out to a RAM while we were upgrading the software, and the computer went to basically the blue screen of death and said, I can't deal with this, and shut down. The backup computer was monitoring all this and said, oh crap, the main computer just shut down. Well, I'm going to shut down everything else and put it in what we call a safe mode. So it powered all the instruments down, powered everything non-essential down, and then turned itself to Earth and said, okay, I'm going to send a signal. It takes about 90 minutes to do all this. And it's going to send a signal to Earth and say, hey, all right, now what do I do? And that's what the backup computer was for. So we got the signal, we started getting telemetry down from it. We worked the problem, we figured out what had happened on the ground. Now remember, we have a 9-hour round trip flight time, an RTLT, to send up a reboot command and wait for it to actually happen. And doing the reboot takes about 2 hours. So it's an 11-hour process just to reboot the computer on the spacecraft. So we had to reboot it actually twice. First time was just to get it up, make sure it was running, and then reboot it again to make sure things got loaded properly. And then we had to reload the flyby sequence. The flyby sequence started on July 7th. The problem was July 4th. We got the spacecraft back up and running on July 6th. Skin of our teeth, we got it going, everything was healthy. We didn't lose any critical science. We lost a couple dozen pre-images of Pluto on approach, but they weren't critical, they weren't absolutely necessary. We were fine living without them. But the critical stuff started on July 7th. And then July 14th, we shot through the plane of the Pluto-Charon system here. And this whole time, we have pretty much no contact with the spacecraft, because the spacecraft doesn't have a gimbal for its antenna to be able to point the instruments at its target and point the antenna back to Earth. It's either pointing everything at the target, or it's turned to Earth and is talking to Earth. It can't do both. So what we did, we had a phone home signal built in after the flyby bit was done. And so while we knew this happened at like 7 in the morning on July 14th, we weren't certain that we didn't actually hit something that we didn't see. And so the rest of the day we were on kind of edge, you might imagine, until about 9 that night, when we got the signal back. And it said, "Hi, I survived. I'll talk to you next week." And that's all we needed. And at that point, things were good. So in order to talk intelligently about surface features on Pluto, we have to name things. These names are all unofficial. They have not been ratified yet by the IAU. We hope that they will take the name suggestions that the New Horizons science team has come up with and say, okay, yes, these will be the names. But the IAU is the governing body that determines what names of features are going to be. So all these names that you see here are unofficial names. But you need to be able to talk about it intelligently. You can't say, well, the big dark area to the left of the big yellowish white area that's just to the left of the blue area right here. You guys know what I'm talking about? Or I could say the Cthulhu ratio, which is this area right here. So all the names that you see that are associated with Pluto or Charon from here out are going to be unofficial names. So the Sputnik Planum. The Sputnik Planum is this big, bright spot in the middle of the field of view of the planet. And it's, if you remember the earlier images of Hubble that I showed, where you saw that brightish area that rotated around, that was the Sputnik Planum. So we could see it, we just didn't know what we were looking at the time. The Sputnik Planum is basically a giant glacier. It's got all kinds of weird stuff going on in it that we don't normally see, but on the edge of it is these rugged highlands. You have these hills that are just out there for some reason. You have the cellular terrain that's all around. The cellular terrain here bounded by these shallow troughs. You've got these random hills, some of them stacked up, clustered together, some of them remote, isolated by themselves. We don't know why. Current theory, one of many, is that they're stuff that was underneath this nitrogen methane ice, and as the nitrogen methane ice is melted or sublimated away, they've come up, they've been exposed. Because at this point, Pluto is in its late summer. It's basically in its August-September phase. A lot of Sputnik Planum is full of these pits here. And this image here, and the next couple you see, are, the resolution is about 80 meters. So these are large pits. And then you can see some of these shallow troughs here that delineate the cellular terrain. and then these isolated hills that are sticking up. You know, one thing about a flyby is you see all this cool stuff and you're frustrated because you can't go back and look at it again from a different angle. You get a one shot and you go, what is that? If I had another instrument I could use or a different angle, then I'd learn more. But it's going to be a few decades before we get that. Meanwhile, we still have all this data to pore over and discuss. Again, this is the Sputnik Planum here. Down here you can see there's clusters of mountains. And up in here you can see where the Sputnik Planum is, the ices are broken up against the highlands here. And you can see, we can tell there's actual flow in the ices around here. Down here, towards the mountains, you have the Hillary Montes and the Norgay Montes. Trivia note for you, the Norgay Montes were the first ones that were named by the science team, and as a rock climber, mountain climber, I personally hope that IAU keeps that name because it's named after Tenzing Norgay, who's the first Sherpa to climb up and back down Everest with Sir Edmund Hillary. And if they keep his name on the planet, his will be the first Tibetan name assigned to an object in the solar system. So these are the Norgay Montes here. If you don't already know, they are 11,000 feet tall. So they're not inconsiderable. They are basically water ice. It is cold enough on Pluto that water ice can form into these mountainous shapes and retain the shape. It won't just slow off. It's nitrogen and methane can't do that. They would just be lumps. They don't have the cohesive power that the water ice does. And if you look further down here, you see there's a depression right here. The Norgay Montes are right here, and this depression right here, and then further south, another one. These are, that we understand, cryovolcanoes. The only two that we know of on Pluto right now. We haven't seen anything else yet, but then again, we still have a lot of data on the recorders that we're trying to get down. But how cool is that? We have cryovolcanoes on Pluto. They weren't erupting when we went by, but that's okay. Back off to the side, you can see these mountains here. I don't remember who they're named after right now. You can see the glacier of Sputnik Planum broken up against it, and you can see the pitted region of the cellular terrain. You can see these rugged mountain landscapes here. And just another trivia note, I have seen some climbers already plot out little routes to go climb and post them online. Got to it before I thought about it. If you're into skiing, we've determined that these white areas here, or these purple areas in this image of the Cthulhu ratio are actually snow-capped mountains. Methane snow-capped mountains. Who wants to go ski methane snow? So this image here is a false color image showing you water ice on Pluto. These are regions that we have determined that there are high concentrations of water ice. Water ice is easily masked by the presence of methane ice. So these regions here either have very low methane ice around or are very, very rich in water ice. You can see the Sputnik Planum here, almost nothing shows through because it's basically a methane nitrogen glacier. More stuff about the glacier. You can see there's an inflow here from the highlands into this alluvial fan-shaped area up here. There's an inflow region here, there's an inflow region here. This was taken when we were directly overhead, and as we flew past, we were taking images looking back at the planet. And this is looking back, so we have a different light angle from the sun, and you can see this channel right here and this channel right here flowing into the Sputnik Planum. So there's active geology happening on Pluto. Another thing that we were very interested in is doing crater counts on the planet. Not just to see how many craters there were that from impacts over the millennia, but very interesting to notice that the Sputnik Planum has no craters in it, which says it's very young. By very young, a million years or so, but all the action that hit Pluto happened before the Sputnik Planum glacier formed. Or it hit the glacier some time in the past, but it has since been, the evidence has been erased because of the activity of the glacier. Going to the north, again, it's a color enhanced, but this is a yellowish material here, and they think this is exposed areas of methane that have been basically solar weathered, and there's no nitrogen up here. There's also these canyons here that are quite long, and these pitted areas here. Another canyon right here. So if I go back, you can see that little canyon there. You see a little canyon here. You can see the big canyon right here. It's very easy to pick out. So the surface of Pluto is tremendously interesting. There's so much different things going on there that you can't shake a stick at it. But there's more. When we flew past Pluto, we looked back. We wanted to study the atmosphere of Pluto. The best way to do that is to look at the light scatter when we're past Pluto, from the light scatter from the sun coming back and being backscattered. And you can see there's this glow right here. And not only is it glow, but if you put color to it, it's actually blue. So Pluto has a bluish sky. Not only that, but if you look closely, these lines here are not JPEG artifacts. They're actual haze layers in Pluto's atmosphere. And Pluto's atmosphere extends up. It pushes out about 1,000 kilometers, which is a little bit more than Earth. But there's all this stuff here. This is the Gate Manches right here. Looking a little bit closer, you can see the different layers here. So there's active weather on Pluto also, not just geology, but active meteorology too. The Gate Manches here, you 11,000 foot tall mountains. If you look down at the terminator of the planet, the day-night transition point, you can see through the haze the shadows of the mountains that are being cast from the sun. So we've learned a lot from just this one little flyby. In measuring the atmosphere, when we flew past Pluto, we were doing, we had planned it so that we would go right behind Pluto relative to the sun. So we could see the light drop off as the sun went through the atmosphere and then behind Pluto, and then came back out again, and it was fully exposed. So if you have an atmosphere, it'll drop off on a curve. If there's no atmosphere, there'll be a sun, darkness. And when we looked for Charon, which we also plotted to go behind for the sun, we saw sun, nothing. So insofar as we are able to determine and can say, Charon has no atmosphere, Pluto has a heck of an atmosphere. All right. So now we'll step away from Pluto for a little bit, and we'll start talking about some of the other bodies around Pluto. Charon was discovered back in 1978 by this gentleman right here. He was looking at images of Charon, and astronomers had seen this bump appear periodically when they looked at Charon, and they said, instrumentation effect. This is a bad data set, and discarded it, because that's what Pluto normally looks like. But this guy here, I'm spacing on his name. He saw this bump, and he thought, well, what if it's really something? And he went back and he looked at data sets that were taken, and he figured out that every 6 days and change, that bump appeared from there, and then on the other side there. And he said, I think we have a moon. And he took it to his supervisor, and the supervisor says, I think we have a moon. And then, the news populated out, and other astronomers started looking and go, oh yeah, we do, we have a moon. That's cool, Pluto now has a moon. We didn't know that it was massive enough to be a binary dwarf planet as opposed to a moon, but at the time, from what we understood of the data, it was a moon of Pluto, which was big news back then. So one of the things we wanted to do was study Charon too. So this is when we were coming in mid-June, about a month out from the flyby. This is the best we could do at that point. And then when we got to the flyby, remember I mentioned that Charon was on the other side of Pluto from where we flew past. So the resolution that we have of Charon is much, much lower than what we got of Pluto. Nevertheless, there's still a lot of stuff here going on. It's not as geologically active as Pluto is. This is a slightly enhanced color image. This is a reddish brown area at the top of, at the North Pole of Charon. You got this, this bisection cliff bands right here. You've got this little, what they call a moated mountain. It looks like a mountain that's been sunk in the terrain. We don't understand that. I was thinking, well, maybe it could be just natural. It impacted really slow. It's very, very. It's got impact craters from various meteoroids and things that have hit it. It's got cliffs. It's got color. There's a lot of things going on here, and we have names for it. Anyway, moving on from Charon, we have other bodies to look at: Styx, Nix, Kerberos, and Hydra. Hydra and Nix are fairly large. They're 20, 40 kilometers across. Styx is less than 10. It's like 9 point something kilometers across. It's tiny. That we could see it from Earth at all. We had to use the Hubble to see it. It is amazing. But we missed it. There, we didn't land. So this is Nix. You can see it's got pits on it from impacts. Larger areas here that possibly could have been an impact. This is a mix of color and black and whites. This is a color-enhanced image of Nix. There's light-ish areas and there's reddish areas on it. Hydra here, you see there's a big pit here, there's a pit right here. There's stuff going on, and that's the best we've got of Styx. Little tiny Styx. What the science team who are studying these bodies thinks happened was Hydra was hit at some point at a glancing blow by something. What that something is, we don't know, but some cosmic interplanetary bullet came by and smacked Hydra on the corner and sent it spinning into this crazy loop here. Everyone else is nice and quiet and quiescent. One theory I've heard from the science team is that these are actually fragment remnants from a large impact of Pluto. These bodies they have a very high albedo. They're very, very bright relative to their size. And it's suspected that possibly something hit Pluto that maybe formed the Pluto-Charon binary pair, and then other stuff was spewed out from the impact. And that stuff either coalesced or it was dispersed into the Kuiper belt, and the stuff that stayed, the larger pieces, formed moons around the Pluto-Charon pair. So that's the nuts and bolts of the Pluto system. New Horizons is still moving out. Remember I mentioned the time delay in just getting a signal back and forth to New Horizons. The further New Horizons travels, the longer the time lag is going to be. Also, how many of you here remember 200 baud modems? I'm serious. 300. We're about a magnitude better at communicating with New Horizons. At the best case, we could go from about 1,000 to 2,000 baud on our connection with New Horizons. So downlinking gigabytes of data takes a while, and time lag and everything else. So it's going to take on the order of 12 to 16 months from the flyby until we have everything down. At this point, I believe we're about 30 or 35% through the tape recorder, through the solid state recorder on getting the data down. So there's a lot more on the recorders that we haven't seen yet. There's a lot more to be discovered. There's a lot more questions that we haven't come up with to ask once we see this data come down. So over the rest of this summer, you're going to see, if you monitor any of the Pluto sites, more cool stuff coming down. Meanwhile, we're not idle. New Horizons is heading towards this object right here with the romantically imaginative name of KBO 2014 MU69. Your task for tonight is to repeat that 3 times fast and come back in the morning and recite that up here. Before the encounter, we started planning for what was going to happen after the encounter. And we only have a little bit of fuel on the spacecraft. The fuel is used to spin the spacecraft up and down, to do any trajectory corrections that we need to do. Unlike Messenger, which has solar panels and was right near the sun, and could use the solar panels as a solar sail to do trajectory corrections, New Horizons has nothing like that, so it has to rely on fuel to retarget itself in any direction. And so we wanted to find something else out in the Kuiper Belt. So we spent a few years using ground-based telescopes looking beyond where Pluto was, where we would be going to see if we could see anything, and we found nothing. We know there's stuff out there, we've detected it from elsewhere in the Kuiper Belt, but that little cone that we could get to, we saw nothing. So we employed Hubble last year, and we got 3 detections of objects. Tiny, tiny objects, 20 kilometers across. They're not Pluto size. And the team sat down and said, well, this one is really not a viable object, but these 2 are, but they're far enough apart we can visit one or we can visit the other. We can't do both. So a decision was made back in September of which one to visit. The proposal was presented to NASA headquarters. NASA headquarters said, okay, you're approved. So we are now en route to meeting KBO 2014 MU69, which will be January of 2019, right at the turn of the year. And then after that, this is a MU69 right here, taken with the Hubble, that right there. It's bright. After that, we'll see. We have enough power on the spacecraft to last until the 2030s, and then the uranium-238 that we have in the RTG will get to a point where we can't use it anymore. And I thank you for your time this evening.